Okay, that's good. Well, let's generalize this. You know, that's what we like to do in math. We like to generalize. So what's actually happening here? Well, there's a few things happening. One thing is the factorial. Namely, if you let n be any positive integer, right? Excuse me. If you let n be any positive integer, then n factorial, okay? By definition, n factorial, it's denoted by n and an exclamation point. This is, by definition, this big product. Essentially, you start at n, you subtract 1 consecutively until you get down to 1, and then you multiply. And that's really all it is. I mean, I guess you could think of 1, when n is 1, 1 factorial you could just think of as 1. Okay? You could think of that as just 1. I guess it's really, the definition if you want. 2, when n is 2, you have 2 factorial. But that's just 2 times 1. 3 factorial, what's that equal to? Well, that's 3 times 2 times 1. Right? 3 times 2 times 1. And then 4 factorial we have here. That's 4 times 3 times 2 times 1, which is 24. Now this might throw you off a bit. This is really more of a definition as well. People just define 0 factorial as 1. That's just, again, part of a definition. 0 factorial is just defined to be 1. Okay, it's really more convention. It's also so that this equation actually holds. This turns out to be very useful. I mean, if you really think about what a factorial is by definition, then this equation is kind of obvious. Although, again, you have to make sure you know that 0 factorial is 1. All right. So this is what we have here. Okay, so that's good. Factorials do come up a fair amount in probability theory. At least in this class they will. That's what a factorial is. Okay. All right, well, that's what's happening in the previous example. So now let's modify that example, a little bit to make things even more interesting. Let's assume now it's still a 5-digit password we're making. But now let's suppose any digit is possible, any of the 10 digits here. So before we just had we just had 1 through 5. These whole numbers. Excuse me, these integers we just had 1 through 5, just to make it simple. Now we're allowing more possibilities. Okay, now remember, with a password, the order matters. Okay, the order matters. That's what happens when you make a password, okay? We also, again, are not allowing repetition. So we're not allowing repetition, so, okay, well then, how many possible passwords can we make? So again, we're making a 5-digit password. Each digit can be any of those 10 digits. We're not allowing repetition now. Well, the idea is really like what we saw earlier. Namely, there are 10 possible digits you can use for the first one. You can't repeat, so whatever you choose, you can't use again. So now you only have 9 choices. Then you go down by 1, because again, now you chose another number. So those 2 you can't use again. You only have 8 choices. And then that's the same for 4 and 5. So we get this. And we're multiplying because, again, we have the counting rule. You could think of this as the number of ways of choosing the first number. That's our first task. And we have the number of ways of choosing the second number. Here we have the number of ways of choosing the third number. That's our third task, and so on. That's what we get. Excuse me. Not only that, we can write this in terms of factorials as so. That's how many passwords there are. Okay, well, here we have a situation where order matters and repetition is not allowed. What we're actually doing is making permutations. Each password is a permutation of these digits, is a possible permutation, I should say. Permutation is an ordered list with no repetition. And that's really, this is again just generalizing what we had from before, what we had in this example. Essentially, if you have n possibility, if we are arranging in order, so order matters, r items out of n possibilities. So there are n possibilities, but you're only arranging r of them without replacement. The order matters. The number of possible arrangements, which again is a permutation, is this. Which turns out to equal this, which is really equal to this here. So, now this is really important, so that's why we have this notation here. P of n comma r. So P of n comma r is the number of permutations of size r out of n possibilities. In other words, this is the number of permutations or the number of ways we can order r items out of n possibilities without replacement. That notation is not the same as what's in the book. Mostly because I couldn't write the book's notation on PowerPoint slides, so I'm using this one. But this is what the book uses, although it's subscripted. I mean, the R I was able to subscript, not here though. The N I wasn't, so that's why I'm using this. Now you could use this notation if you want. It turns out this one with the factorials is a lot nicer. I think also it's easier to see like where the numbers come from. Okay. Basically, if you have this though in your calculator, I know Desmos has a calculator built into it, and they use the book's notation. You enter your N first and a comma, then you type in R, and you press enter. I'll show you near the end of class. That's what happens. So again, this is without replacement, so no repetition, and order matters. But what if we allowed repetition? Right? The very first example, order mattered. You know, we were making passwords, but we allowed repetitions. Right? We got 5 to a power. Well, it turns out in such a case, if you're arranging R items out of n possibilities, so we're arranging R items out of n possibilities, the total number then is n to the r. This is order matters, but we allow repetition. Again, it's just the basic counting rule, or the counting, whatever this book calls it. Same thing. You're just basically multiplying. That's all. Okay. All right, so let's do some examples of that. Actually, before I do that, are there any questions? At all? Oh, someone has a question. Yeah. Oh, R, you're arranging R items out of n possibilities. So R is how big how many items are in the list, or how many items there are in the permutation. Or okay, it does. Okay, good. I was a little concerned that didn't make sense, but we'll do some examples as well. So hopefully that should help. Good question though. But for instance, if you maybe this will help as well. If we go back to here. So in this example with the passwords, right? R would be 5 because each password is 5 units long. Okay, and the number of possibilities is 10, so N would be 10. So the number of possibilities is N, and how big the list is, or how big the what do you call it, the arrangement is, that would be R. We better do some examples because I think that would make it better.